We have only so far been able to touch on the very basic concepts of designing intelligent search trees, and research to date is much more advanced. So you might be wondering, considering the state of the art, how low can you go? What are the best search tree algorithms to date that we know of? And actually, I'm not going to tell you anything about vertex cover for now, because that problem will deserve a little more attention later in this unit. I will show you the state of the art for some other problems. So for independent set, there are currently two algorithms that could kind of consider to be the smallest search trees. One has size 1.189 to the power of n, and the other one has size 1.211 to the power of n. It's two different algorithms. This here has a bit larger search tree, but the algorithm itself is probably a little bit faster in the worst case than this one here because of the polynomial factors that are involved. But this here is just the search tree size. For click, well, it's the same as independent set as always because of the close connectedness of those two problems. In one of the previous units, you also got to know 3sat, which is a satisfiability problem where every clause has exactly 3 variables, and that can be solved with a search tree of 1.496 to the power of n last time I checked. This is a very advanced search tree. It's basically half a book of proofs required to show this here. Now, what about shortest tour, or more generally, the traveling salesman problem, which is shortest tour, only that you can only visit a city exactly once? And this is a very interesting one because the best, well, it's not even really a search tree, but the best algorithm has an exponential factor of 2 to the power of n. So here, it's still an open research problem to find out if you can design better search algorithms for this problem. By the way, in case you're wondering, do the laws of NP completeness, as far as we know them, say anything about how low the exponent can go? So really put a limit on the space here. Say, for example, unless p equals np, there's no algorithm for independent set with a running time of, or with a search tree that is smaller than 1.1 to the power of n or something like that. And the answer here is, we don't know. So it might be that you can solve independent set, for example, in an algorithm with 1.01 to the power of n as your search tree size. Nothing in the laws of NP completeness that would speak against that.